what we see is that for different sizes of sample sets, our proposed approach always achieves a smaller regret overhaul, meaning that our solutions are better suited to approximate any solution that wasn't sampled. In another experiment, we looked how the output of our algorithm can be used in a reward learning application. So here we use reward learning using a framework learning from choice. So we want to learn a reward function from a user by showing them two alternatives at a time, and they pick the one that they like better. And so we do this over 10 iterations, and we hope that we will learn their reward function and then be able to compute an optimal trajectory for that user. And let's just worry about the colors, not about the different shades in it. So Blue is using this simple, using an algorithm for learning from choice with uniform pre-sample. So we just uniformly sample a bunch of possible solutions and then give that to the algorithm. And Orange is using our pre-samples, the output of our algorithm. And we observe that with our samples, learning is faster, and it actually is able to find better solutions. So if you use uniform pre-samples, your pre-sample set might not contain a close to optimal solution, so you converge to a local optimum. But with our set of pre-samples, we actually have a higher chance of finding the actual optimal solution for a certain user. Okay, with that, I'm at the end of the main part. So in summary, I presented to you an algorithm on how we can find good scalarization weights for a linearly scalarized multi-objective optimization problem. And we find weights that in the end allow us to approximate any trade-off in the linear scalarization. Of course, this is not the end of it. We have some limitations in our work. I guess the biggest limitation is that we require an exact solver for the scalarized optimization problem. And that's not always the case. So we want to extend the work in two directions here. First, we need to consider that we only have a suboptimal solver, but it will break our concavity result. So we need a mode, or like some little trick to repair the concavity so that our algorithm works. Secondly, if that suboptimal solver happens to be an approximation algorithm, it would be very nice if that approximation factor carries over into our regret bound. Secondly, we only focus on linear scalarization, which is widely used, but it's not Pareto complete. So you can't recover the entire Pareto front with a linear scalarization. Therefore, we also want to look into Chebyshev scalarization, which is Pareto complete, and adapt our algorithm to that setting. And finally, we also want to study the special case k = 1. So we're only allowed to pick one sample and solve this one-size-fits-all type of problem. The good news is the first 3 bullets, we are on a very good way of having answers for that. So the proofs are written out. We just need to write a paper about that. With that, I would like to conclude, and thank you very much.
Our next speaker is Brian. Brian is. He's going to talk first today. Began at MIT working with Leslie Paxton.
Test. Can everyone hear me? Take mascot to this. I'm going to be speaking to everyone today about motion planning with uncertainty over obstacle locations and extents. And let's go ahead and dive in. So just a little bit of brief background. So we're going to start out, we all know that motion planning can be a hard problem. We have a bunch of hardness proofs, but at the same time, we're often able to solve motion planning problems in practice. And there's a bunch of algorithms that are able to do this. We have sampling-based algorithms, optimization-based algorithms, search-based algorithms. And the basic idea that we have behind all of them is that there's a lot of the cases that we encounter in practice are not really the hardest possible motion planning problems. So there's a bunch of heuristics and different kind of algorithms designs that we have that are actually able to solve a lot of the problems that we see. Right, so the fact that we have these hardness results for motion planning problems wasn't kind of the end of the story there. We're still able to make useful progress. So At the same time, we have prior results that say motion planning with obstacle uncertainty is in some ways harder than vanilla motion planning. And so one way that we can look at this is even if I give you a graph that I tell you contains the solution to this kind of motion planning problem, it still ends up being hard to find that solution even constrained within that graph. So we'll jump into a little bit more. But we have this problem becomes harder if you have obstacle uncertainty than the original problem was. But at the same time, we have these problems, so we still want to be able to solve them, right? We don't want to just give up. And that's going to be the focus of the talk today, is how can we make some progress even though we have stronger hardness results that are blocking algorithms that look similar to a lot of the algorithms that we're used to seeing. So let's go ahead and kind of motivate the problem in a little bit more detail. Say you're this robot and you want to get to the green dot, but your glasses are a little foggy, your sensors are noisy. You don't know exactly the location and shape of the obstacles that you're encountering in your environment. So the way that we're going to formalize this is that you have some sort of distribution that these obstacles are drawn from, and you draw the obstacle kind of once at the beginning of the episode, and the obstacle remains static, even though you don't know its exact location. And your goal is to find a path that has low collision probability to get to, in this case, the green star. And this, I want to point out a couple of little things that are going on here. So in particular, because you only draw the obstacles once at the beginning of the episode, say that you kind of stopped at some particular iteration and stay there for a while, say some number of waypoints. Your collision risk isn't going to increase, right? Because the obstacles are static, you're not moving, right? So we're going to lean into this assumption that these obstacles are static and they're kind of only drawn once. And kind of in particular, this turns out to give us strong correlations of what the collision probabilities are between points that are kind of close locally in the space that we're looking at. And so I also want to give you a little bit more intuition of why this problem is harder than the motion planning problem with known obstacle locations, and give you a little bit more intuition for the kind of correlations and collision probabilities that we might expect to see in practice. So let's take a quick look at the green dot and the purple dot. Each one of those is going to have an epsilon probability of collision with the obstacle that we see on our left. And the question we want to ask is, what is the probability that at least one of the two dots is in collision, either the green dot or the blue dot or both? And if we look closely at the obstacle, kind of the obstacle on the left, of which we drew a couple of draws from the distribution, we can see that, we have a good sense of the shape of the object, what the angle of that side is, but we don't have that good of an idea of what its extent is on the x-axis. That's really where most of the uncertainty is. And what that gives us is, we could go ahead and use a union bound and say, okay, one way that we can bound the probability that either the green or the blue point is in collision is say it's just 2 epsilon. But because we're mainly uncertain about this position on the x-axis, there's actually a strong correlation between the event that the two are in collision, right? Because if that obstacle ends up further to the right than we expected, we're more likely than not, both the green point and the blue point are going to be in collision. So kind of in this example, we can see that actually the real probability of that either the green or the blue is in collision is only going to be about epsilon. It will be a little bit more. So this kind of means that we have to be thinking quite a bit about the correlations in collision probabilities between points, especially ones that are kind of close in the space that we care about. So let's give an example that involves some trajectories and try to motivate a little bit why the kind of motion planning problem that comes out of this is harder, even if I give you a graph that contains the solution. So again, you're the robot, you're trying to get to the green star. And there's 2 paths that you can take. You have to take the green path to get there. But to get to the start of the green path, you can take the red path or the blue path. And the main difference in the red path and the blue path is which obstacles they interact with. The blue path, if you look at it in isolation, is a little bit more risky. But the red path interacts with that obstacle on the right, as well as the other three obstacles. And in this case, even though the individual, if I took and sum up the risks, the red path and the green path would be a lower risk path than taking the blue path and the green path. That ends up being kind of not the best, that ends up being a very loose approximation. The main risk of collision in these paths right here is that obstacle on the left. And because that collision probability is actually correlated between the blue path and the green path, it actually ends up being lower risk in this case to take the blue path and then the green path, right? Because instead of taking kind of a bunch of independent bets that you have good estimates of a bunch of different obstacles, you're essentially choosing, I only want to be risky with respect to a smaller set of obstacles. And that allows you to reduce the total risk of your trajectory. So, right, we want to lean into the fact that we have these correlations and take advantage of them to find trajectories that are both less risky and also not as conservative, right? Because we don't want to end up with a system that is just scared of going near objects because it's always afraid it's going to collide, right? So we want to have some sort of balance between the system being conservative and actually kind of having a low probability of collision. Now, if you're trying to go and do this kind of planning, right, you can say, okay, in this case, we don't have a lot of obstacles. We can just remember which obstacles we interacted with in the past, right? We can see, oh, that obstacle on the left, we've already been by it once. But it turns out that is exactly the thing that increases the computational complexity of the task. Right, it's the fact that in the worst case, and you can kind of construct reductions, and we've done that in a prior work, that show that you can actually be forced to memorize a bunch of the previous obstacles that you went by, and you can actually go ahead and take this all the way to constructing an NP hardness proof, right? But at the same time, right, does that mean that all the problems we encounter require long memory? You know, say that you're driving in some sort of parking lot and you're figuring out the path that you're going to take. You don't kind of remember every single car that you might go next to as you're like planning some part of the trajectory that's way far out, right? Usually when you as a human are kind of planning these sort of tasks, you really only have to think about things that are local. You don't have to come back to these obstacles many times. So the idea here is know that these problems don't all require long memory, and we want to design an algorithm that can take advantage of this and be able to quantify this. So for that, we define something which we call the collision horizon, which measures the complexity of a problem instance. So basically, it's going to be, this collision horizon is going to be a parameter of our algorithm. And when the collision horizon is going to be small for an instance, it's going to be an easy problem, and our algorithm can solve it efficiently. And when the collision horizon is large, we have a hard problem, and our algorithm isn't going to be able to solve it as efficiently. So the basic idea behind the collision horizon is it's in some sense a way of measuring of how many obstacles we need to encounter between interactions with the same obstacle. And this ends up driving kind of how much memory we need to have. So we have a little example here where we have these three obstacles. We have a sun, a cloud, and the moon. And in this case, the one thing that we're uncertain about, right? In this case, we know exactly where these obstacles are. We're just uncertain about how big they are, you know, just for our cartoon example. So it might turn out that the sun is actually twice as big as we expected, right? And that's kind of where our collision risk is coming from. So if we go ahead and look at this trajectory right here, we can see, you know, we're really only getting close to one obstacle of the sun, right? And the start and the end of the trajectory, we can see they're correlated. If, you know, the only thing we're uncertain about is the size of the obstacle. And in this case, because we're only interacting with one obstacle, the collision horizon we're going to say is 1. But if we wanted to go ahead and take this longer path that goes past the cloud, the moon, and then kind of around, we can see between the times that we return to the sun, we encounter 2 additional obstacles. And that makes our collision horizon 3. because to properly